Hey guys, today we're going to learn about implicit differentiation. Now, implicit differentiation is being able to take the derivative of what's called an implicitly defined equation. Now, what's an implicit equation? We need to understand the difference between an explicit equation and an implicit equation. An explicit equation are like the equations that we have been working with, such that y can be isolated on one side of the equation, and it is clear that the equation is a function, meaning that y is going to equal to one particular number. For an implicit equation, that means that the equation cannot be written in terms of y, and it's going to be almost impossible to solve for y, meaning that that equation does not represent a function, and there would be more than one y value per x value. So here are some examples. This is an explicit equation, and we've learned how to find the derivative of an explicit equation. So let's practice that. We have y equals the square root of 25 minus x squared, which is equivalent to 25 minus x squared raised to the 1/2. Now again, this is an explicit equation because we clearly see that y is solved for here and it has been isolated. When I take the derivative, we would find y prime, which, just so you understand notation in the future of this lesson, y prime is the same thing as dy dx, which means the derivative of y with respect to x. So when I take the derivative here, this is going to be the chain rule. So I bring the 1/2 to the front, leave the inside alone, subtract 1 from the exponent, and multiply by the derivative of what's inside the parentheses, which is negative 2x. Here, the 1/2 and the 2 can cancel out. This 25 minus x squared to the negative 1/2 is going to go down to the denominator. So my derivative is going to be negative x over the square root of 25 minus x squared. Now over here, this is an implicit function, because if I were to try to solve for y, I would have to subtract the x squared, and we get y squared is equal to 25 minus x squared, and then square root. Now whenever we take the action of square rooting, we always have to make sure that our answer is plus or minus, which means that y has two equations. It would be the positive square root of 25 minus x squared and the negative square root of 25 minus x squared. So this is two separate equations that represent y. So I would not be able to find the derivative if I were to solve for y because there are two equations. When that happens, then what we have to do is just take the derivative directly from the equation as it's written. Whenever we are going to find the derivative, we do this like normal, right? The derivative of 2x is of x squared is 2x plus. Now we do the same thing for the y. The only thing is, think of this as chain rule. We are finding the derivative in terms of x. So that means that whenever we take that derivative, the derivative of the x is, like we do our regular rules. But y is not an x, so when I take the derivative, that would be 2y, I would have to multiply it by the derivative of y, which is dy dx. Kind of like chain rule. You know how like if you have, let's say f of x squared, the derivative would be 2f of x, and then subtract 1 from the exponent, and then multiply by the derivative of the inside here, which is f prime. So that's the same scenario that we have here. Y is kind of like an f of x. So we have to apply the chain rule. So that's 2y times dy dx is equal to, and the derivative of 25 is 0. Once you have this, our goal, remember that our derivative is dy dx. This is what I want to solve for. So we're going to isolate that dy dx. So I'm going to subtract this 2x over to the other side. We get 2y dy dx is equal to negative 2x. And then we divide the 2y to isolate that dy dx. So my derivative, dy dx, is going to equal to negative x over y, since these 2's here can cancel out. And that's basically the process of how you find the derivative of an implicit function. So I put here, when finding the derivative of an implicit function, you derive like normal, but anytime you are finding the derivative of y, you must multiply what you get with dy dx. So let's practice. Here we have a circle, and circles are implicit functions, because if I were to draw a vertical line, I would go through 2 separate points, meaning that a circle is not considered a function. Therefore, this is an implicit equation. We're going to take this derivative. We have x minus 3 squared plus y minus 2 squared is equal to 25. This is the equation of this circle. And just so you know, the equation of a circle is x minus h squared plus y minus k squared is equal to the radius squared. The h and the k is the center of the circle. We can see that the center is at 3, 2, so that's why this is 3 and this is 2. And then the radius is 1, 2, 3, 4, 5. So if you square it, you get 25. So that's how you get the equation of a circle, just so you know. Now let's find the derivative. I would have to apply the chain rule for each of these parts. When I apply the chain rule here, this would be 2 x minus 3 times the derivative of the inside, which is 1, plus 2 y minus 2. The derivative of the inside, we have a y, so this is dy dx is equal to 0. And now I'm going to isolate dy dx. So I'm going to subtract this 2 x minus 3. You can distribute it if you like, I just didn't. And then we have 2 y minus 2 dy dx is equal to negative 2 x minus 3. And then I'm going to divide by 2 y minus 2. Like this, my 2's here will cancel out. And I have that my derivative, dy dx, is equal to negative x minus 3 over y minus 2. So now, if I wanted to find the slope of our tangent line at a particular point, notice that here we have coordinates. So what we're going to do is we're going to plug in the coordinate into my derivative equation, and that's going to give me the slope of the tangent line at that particular coordinate. So think of this as your point of tangency. If I plug in negative 1 into this equation for my x and 5 as my y, we get negative 1 minus 3 over 5 minus 2. Negative 1 minus 3 is negative 4, and then the negative outside will make it a positive 4 over 3. So because this is a positive value, that means that at negative 1 comma 5, my graph should be increasing. Now let's look at my function. Here's negative 1 comma 5. And you can see here that the circle is going up. This would be my tangent line. So you see how it's positive. My function, or rather my graph here, is increasing. If I take 3, 7 and I plug it into my derivative, I get negative 3 minus 3 over 7 minus 2. So again, since we have a coordinate, we got to make sure that we plug in the x where the x is and the y where the y is. And this is going to give me 0 over 5, which is 0. If my derivative is equal to 0, that means that I must have a horizontal tangent. Now let's check that on the graph. At 3, 7, 1, 2, 3, and then this is 2, 5, 7 right here. Here we have a maximum. Therefore, I have that horizontal tangent. Now let's try 6, 6. If I plug in 6 into my derivative, I get negative 6 minus 3 over 6 minus 2. 6 minus 3 is 3, and then negative over 6 minus 2, which is 4. Because this is a negative derivative, that means that my graph should be decreasing. So I'm going to come here and check out that coordinate. So here's 6, 6, and you can see that it is decreasing. Now let's test out 8, 2. If I plug in 8, 2 into my derivative, that is negative 8 minus 3 over 2 minus 2, which we end up with negative 5 over 0, which is undefined. Now, whenever you have 0 in the denominator and you have an undefined slope, that means that we're going to have a vertical tangent line. And if you look at this coordinate at 8, 2, you see how the graph here, if I were to draw the tangent line, it would end up being vertical. So if 0 is in the numerator, that means you have a horizontal tangent line and there's the presence of either a maximum or a minimum. Or if the denominator is 0, that means that we have a vertical tangent line. And just like with the others, a positive derivative means that the graph would be increasing, and a negative derivative means that the graph would be decreasing. Now we're going to come back to all this information, but let's now practice just finding implicit derivatives. So we got here y squared is equal to 2x plus 3y. Let's take that derivative. We would get 2y and always multiply by dy dx is equal to 2 plus 3, which is the derivative of 3y, and then multiply by dy dx. I want to get all of my dy dx's over to one side of the equation. So I'm going to subtract this 3 dy dx over to the other side. So what I have here is 2y dy dx minus 3 dy dx equals 2. Once you have all of your dy dx's on one side, what we do then is that we factor out the dy dx, since that is a common factor. So dy dx, and then I open my parentheses. I already took out the dy dx, so I have this 2y minus 3. And that's going to equal to 2. Now I divide. So my derivative, dy dx, is going to equal to 2 over 2y minus 3. Let's try this other one here. We got here the derivative of 2x would be 2, plus the derivative of e to the y is the derivative of the exponent, and the derivative of y is 1, and then I'm going to multiply by dy dx, e to the y. Remember, then we multiply by the exponential itself, is equal to the derivative of x squared, which is 2x, minus the derivative of y squared, which is 2y dy dx. Now we want to get all of the dy dx's over on one side and everything else on the other. So I'm going to add this 2y dy dx. And I want to move this 2 over to the other side. So I'm going to subtract this 2. So now on the left side of my equation, I have the e to the y dy dx plus 2y dy dx is going to equal to 2x minus 2. Now that you have all your dy dx's on one side, we're going to factor it out. And inside my parentheses, I'm left with the e to the y plus 2y. And that's going to equal to 2x minus 2. Lastly, we divide the factor that's being multiplied to the dy dx. So my derivative, dy dx, is going to equal to 2x minus 2 over e to the y plus 2y. Let's try a couple more complicated ones. With this first one, we got 2xy is equal to 3y squared plus 2x. When you have x and y being multiplied, here we have to use the product rule. So that's what we're going to start off with. And think of it as 2x times y. So the derivative of 2x is 2, leave y alone. Plus, now leave 2x alone, and the derivative of y is dy dx. And that's going to equal to 6y dy dx plus 2. We're going to move all of the dy dx's over to one side. And then everything else over to the other side. So on the left, I have 2x dy dx minus 6y dy dx is going to equal to 2 minus 2y. Now we can factor out the dy dx. And we get 2x minus 6y is going to equal to 2 minus 2y. And finally, we divide. So my derivative, dy dx, is equal to 2 minus 2y over 2x minus 6y. Now this is the answer. However, if you wanted to simplify, notice that all of the numbers in every term is divisible by 2. So I can divide every single number by 2, which will give me 1 minus y over 2 minus 3y. Either of these answers would be acceptable. Let's try this one more. When I take the derivative here, this is 15x plus the derivative of 3, which is 0, is equal to 2 and then dy dx. Now for this next part, we have minus this product. What I like to do at this point is I leave the negative and then I open parentheses and I take this product rule. So in that way, I don't get confused when it comes to what's going to be negative and what's positive. So once I do the product rule, then I'll go ahead and distribute that negative. So when I take this derivative, remember the derivative first, so the derivative of 3x squared is 6x, leave y alone, plus 3x squared, and now the derivative of y, which is dy dx. Now I'm going to distribute this negative. So we got 15x is equal to 2 dy dx minus 6xy minus 3x squared dy dx. Now I want all of my dy dx's on one side and everything else over on the other side. As you can see, all of my dy dx's are already on the right side. So I'm going to add this 6xy over to this side and keep my dy dx's there. So we have 15x plus 6xy is equal to 2 dy dx minus 3x squared dy dx. Now I can factor out that dy dx, which would give me, in parentheses, 2 minus 3x squared. And finally, we would divide the 2 minus 3x squared. So my derivative, dy dx, is going to equal to 15x plus 6xy over 2 minus 3x squared. Now let's have a look at putting all of this together. Consider the curve given by xy squared minus x to the third y is equal to 6. For part A, we're going to show that dy dx is equal to 3x squared y minus y squared over 2xy minus x to the third. So here's my answer for the derivative. We're going to make sure that we get that same answer. So here's my function. Let's go ahead and take that derivative. Both of these parts here are product rules. So I got to separate them as one function and another. Oops. Now because this is minus, I'm going to apply the product rule for this. And then I'll distribute the negative after. So the derivative of xy squared, the derivative of x is 1, leave y squared alone, plus leave x alone, and the derivative of y squared is 2y dy dx, minus the derivative of x to the third is 3x squared, leave y alone, plus, let me open parentheses there so I don't forget to distribute the negative, plus now leave x to the third alone, and the derivative of y is dy dx. And that is going to equal 0. So let's clean this up a little bit so we can isolate the dy dx's. We got y squared plus, now our numbers should always move to the front, our coefficients. So this would be plus 2xy dy dx. Now I'm going to distribute the negative, minus 3x squared minus x to the third dy dx is equal to 0. All of my dy dx's are already on this side, so I'm going to move these two terms over to the other. So I'm going to add this 3x squared and subtract this y squared. So on the left, I have 2xy dy dx minus x to the third dy dx is equal to 3x squared minus y squared. Now we factor the dy dx, and that'll give us 2xy minus x to the third is equal to 3x squared minus y squared. And finally, divide. And you can see that what we got here is exactly what's here. So that's my derivative. For part B, it says find all points on the curve whose x-coordinate is 1. Write an equation for the tangent line at each of these points. So the first thing that we have to do whenever we're writing the equation of the tangent line is we're going to find our point of tangency. In this case, we may have 2. And then find the slope at each one. So we're going to plug in x is equal to 1. So when I do that, I get 1. Remember, we're plugging it in here to solve for y. We get 1 times y squared minus 1 to the third, which is 1, times y is equal to 6. What you're going to end up with is essentially a quadratic equation. This is y squared minus y is equal to 6, and we want to make it equal to 0. So I'm going to subtract the 6 over to the other side and make it equal 0. You always, whenever you have a quadratic, especially if you have your variable that's squared and another variable that's not, make it equal to 0 so that you can factor. Now we're going to factor this. Y squared minus y minus 6 is factored to be y minus 3, y plus 2. Since negative 3 times 2 is negative 6, and negative 3 plus 2 is negative 1. Now we solve for y. We get here that y is equal to positive 3 and negative 2. since remember, it's because we set those factors both equal to 0 and then solve for y. So if y minus 3 equals 0, we have to add the 3, giving me the positive 3. And if y plus 2 equals 0, we'd have to subtract the 2, which gives you negative 2. So what does this mean? This means that we have these 2 points of tangency. And we plugged in x is equal to 1, and we got these 2 y values. So that means that my points are 1, 3 and 1, negative 2. See, these are my x's, the 1s, and then the 2 y's that I solved for that x. Now we're going to need our slopes so that we can write the equations for each one. So we're going to find the slope dy dx for when x, for the coordinate 1, 3. So this is my notation, so I know what derivative I'm solving for, dy dx, and then I put a bar, and then I put the coordinate on the bottom. That's letting me know I'm finding the derivative at this particular point. And this is going to equal to, now I found my derivative here, so I'm going to plug in x is 1 and y is 3. That's going to be 3 times 1 squared, which is 3, minus y squared, so 3 squared, which is 9, over 2 times x times y minus 1 to the third, which is 1. So it's going to be 3 minus 9 over 6 minus 1, right? 2 times 1 times 3 is 6, minus 1 is 5. 3 minus 9 is negative 6 over 5. So this is my slope for 1, 3. So then the equation of that tangent line is y minus 3 is equal to negative 6 over 5, x minus 1. Now we're going to do this exact same thing, but for this coordinate, for 1, negative 2. So I'm going to solve for my dy dx for that coordinate 1, negative 2. I plug it in here. 3 times 1 squared is 3, minus negative 2 squared over 2 times 1 times negative 2 minus 1 to the third. So that's going to give me 3 minus negative 2 squared is 4 over 2 times 1 times negative 2 is negative 4 minus 1 is negative 5. So this gives me negative 1 over negative 5, which is 1 over 5. So this is my slope for this point. So the equation of that tangent line would be y plus 2 is equal to 1 over 5 x minus 1. Now let's have a look at finding horizontal and vertical tangent lines. Starting with horizontal tangent lines, a horizontal tangent line occurs when your derivative is equal to 0. In terms of implicitly defined functions, you can find a horizontal tangent line by setting the numerator of the derivative equal to 0. And once you have that particular x, then we would plug it in back into the function to get the y value. So if you look here, it says find the coordinates. So that means that we're looking for both an x and a y, where the curve 4x squared plus y squared minus 8x plus 4y plus 4 is equal to 0 has a horizontal tangent. So let's start off by taking that derivative. The derivative is going to be 8x plus 2y dy dx minus 8 plus 4 dy dx, and the derivative for 0 is equal to 0. So we want all the dy dx's on one side, which they are, and so now I'm going to subtract this 8x over to the other side and add the 8. So that way everything else is on the other side. So we got 2y dy dx plus 4 dy dx is equal to negative 8x plus 8. Factor out the dy dx, and we get 2y plus 4 is equal to negative 8x plus 8. Finally, to get the derivative, we are going to divide by 2y plus 4. So that's my dy dx, negative 8x plus 8 over 2y plus 4. For a horizontal tangent, that means that my derivative is going to equal to 0. As long as the numerator is equal to 0, it does not matter what the denominator is because 0 divided by anything is 0. So to find a horizontal tangent, we set the numerator, the negative 8x plus 8, equal to 0. And now we're going to solve for whatever variable is in the numerator. In this case, it's x. So I subtract the 8, and we get negative 8x is equal to negative 8, and then divide the negative 8. So x equals 1. But again, I want the coordinates. Now that I have my x value, what I can do is plug in the x back into the original function to figure out what y is equal to. So we're going to plug in x is equal to 1. So that's 4 times 1 squared plus y squared minus 8 times 1 plus 4y plus 4 equals 0. Let's simplify this. 4 times 1 squared is 4 plus y squared minus 8 plus 4y plus 4. At this point, we want to, as we can see, this is a quadratic equation. So we want to simplify this and write it in standard form, meaning starting with the highest exponent. So we got y squared plus 4y, and then we have 4 minus 8, which is negative 4, plus 4 would be 0. So this equals to 0. Whenever, at this point, most of the time you're going to end up with a quadratic. So you're going to have to factor. Y squared and y both have a y in common, so I can take out the y, and I get y plus 4. And then once you're factored, you take each individual factor and you make it equal to 0. So you can solve for y. So here, y is equal to 0. And then here I'm going to subtract 4, and we get y is equal to negative 4. So what does this mean? This means that for that 1x, we actually have two coordinates where the curve is going to have a horizontal tangent, one of which is at 1, because that's my x, 0, that's my y, and then also 1 and negative 4. So for this 1x, we ended up with two y's, so those are my two coordinates. And that's how you find the horizontal tangent. Now, for a vertical tangent, it's essentially the same thing. We're going to go through the exact same process, but instead of setting the numerator equal to 0, a vertical tangent occurs when the derivative is undefined. And the derivative is undefined if you end up with, doesn't matter what's in the numerator, if the denominator is 0. So we're going to start off just like in the previous question by taking the derivative of my equation. So we got x squared minus 10x plus y squared is equal to 8y minus 25. So let's take that derivative. This would be 2x minus 10 plus 2y dy dx is equal to 8 dy dx, and the derivative of negative 25 is 0. I want all of my dy dx's on one side, so I'm going to subtract this 2y dy dx, because that way everything else would be on the other. So we have 2x minus 10 is equal to 8 dy dx minus 2y dy dx. Now that we have that all on one side, we are going to factor out the dy dx. So 2x minus 10 is equal to dy dx times 8 minus 2y. And finally, we're going to divide by 8 minus 2y. So that's my derivative. Dy dx is equal to 2x minus 10 over 8 minus 2y. Now we're going to figure out where we're going to have a vertical tangent. We have a vertical tangent as long as the denominator is equal to 0. So 8 minus 2y equals 0. Now we solve for y. So notice that depending on your derivative, your x's and your y's could be either in the numerator, the denominator, like they can switch. You're always just going to solve for the variable of wherever it is you're looking for. So if I'm doing my vertical tangent, you're solving for whatever variable is in the denominator. If you're looking for your horizontal tangent, that means you're solving for whatever variable is in the numerator. It does not matter. Now here, I'm going to subtract the 8. So negative 2y is equal to negative 8. And then divide the negative 2. So y is equal to positive 4. Now I'm going to take that 4 and I'm going to plug it back into my function here in order to solve for x so I can get that coordinate, or rather coordinates. So x squared minus 10x plus 4 squared is equal to 8 times 4 minus 25. Let's work this out now. X squared minus 10x plus 16 is equal to 32 minus 25. And 32 minus 25 is 7. So I want to make this equal to 0 since this is a quadratic. So I'm going to subtract this 7. And I get x squared minus 10x plus 9 is equal to 0. Now we factor. X squared minus 10x plus 9 is x minus 9, x minus 1. Since negative 9 times negative 1 is positive 9, and negative 9 plus negative 1 gives you negative 10. And now we make each individual factor equal to 0. And we get that x is equal to 9, and x is equal to 1. So we now have two x values for the same y value. So our coordinates where we have vertical tangent lines are the x is 9 with the y of 4, and the x is 1 with the y of 4 as well. So that's finding tangent lines, both vertical, horizontal, and at particular points of implicit functions.